Hey there, this is a calculus class. Now, Calc 1 usually meets as a live Zoom class, and today's lesson is a really cool interdisciplinary connection to physics, and it's relatively easy to understand. So it's going to be our calculus introduction video for our online learning initiative. So for our class, we go over the answers. Section 6.3, your homework, and as calculus, you only have 2 questions. It might take you an hour to do 2 questions, but do a homework check. 3 is 6 pi over 7, and 11 is 768 pi over 7. So check or change and questions on that. So the lesson, open up your books to page 446. We are doing work. And I want you to think of physics work. So we know back from Physics 101, we got work equals force times distance. Force times distance there. And so we have an example 1 where, what if I have a 1.2 kilogram book and I'm asked to set that book up on a table that is 0.7 meters high up off of the ground, and we know that the acceleration due to gravity is downward 9.8 meters per second squared. So we're asked to find the work of this problem of lifting the book and putting it on the table. And we know our work equation, W equals FD. And we also know our force equation. So our book, that is a mass. That is not a weight. Remember, mass doesn't have gravity affecting it yet. So we have our mass is the 1.2 kilograms times the acceleration due to gravity, 9.8. And that'll give us our force in newtons, 11.76 newtons being our force. Now we can use F in our equation there for our work. We've got our force, 11.76 for F, and our D, our distance that was given, our height of 0.7. So 11.76 times 0.7 giving us 8.2 joules. Our unit of work in physics is joules, capital J. Now part B, it says, well, what if we have a force of 20 pounds? 20 pounds, notice we weren't dealing with pounds before. So we have a force already in pounds, meaning that 9.8 acceleration due to gravity is already accounted for. Weight in pounds already has gravity in it, so don't multiply by 9.8 in this B, example B here. So we want to know work, and we know our distance is 6. Sorry, that was our other given. A force is 20 pounds, and your distance that you're moving this force or lifting this, using this force is 6. I think 6 feet. I should have labeled my units, 6 feet. And we want to know the work. So we have our equation, work is force times distance. Like I said, our force is already, it's a 20. Do not multiply it by 9.8 because the clue, pounds, tells you that 9.8 acceleration is already accounted for in that 20. And so 20 times our distance, which is 6, giving us 120 feet-pounds. I should have added my feet on my 6 there. There we go. Feet on the 6. Okay, and that's your answer. Now, this is physics. This is your basic. We have a constant force. We have a constant work. We have, let's see. So these equations, they define work as long as the force is constant. But what happens if the force is variable? So we're changing the force. What if we have a variable force? And thinking of a variable force, meaning something that changes, like this quadratic equation. If I'm looking at this, I'm going a little slower, and then my rate of change is increasing and increasing and increasing, and we have this very much changing rate. So we have now a variable force. We're changing the force. So we can't use those equations anymore. Well, we can, but we now have to account for the changing force. So that's where calculus comes in. So here we go. And recently we've gone over it. We're looking for things from A to B. So keep in mind we're picking a bunch of different x's on the interval between A and B will be kind of like restricting the x's like in a certain domain. So we're looking at x's between a and b. Okay, so example 2, and we are given a force, and we are asked to find the work, and we're also given our a and b. So we have, when a particle is located a distance x feet from the origin, a force of x squared plus 2x pounds acts on it. How much work is being done in moving it from x equals 1 to x equals 3? And so we're looking for work, so I have w equals question mark. We know our force, which is a changing force now, a variable, x squared plus 2x, and we're looking at that from when x is 1 to x is 3, and that's from a to b, right there, from a to b. So our a is 1 and our b is 3 there. So we have a formula, or kind of a definition, if you will, and that definition says that we can take an integral. I'll write this down for us. This is in a red box on page 447 for those of you with a book watching this. So the integral we have from a on the bottom, from a to b. So we have that integral symbol, right? The integral from a to b. The function, so f of x is our function, times, or with dx next to it. So the integral from a to b, f of x, dx. So now I'm going to plug in what we know. I know my a is 1, my b is 3, my function, my f of x, is the force, x squared plus 2x. So I'm going to plug that binomial in for the f of x, and then write the dx next to it. There we go. So we've done that. I've written the integral from 1 to 3. We've replaced f of x with the force, x squared plus 2x, and we have dx. And remember, that means derivative. So we are now taking the derivative of this and following the rules there. So this is x, the exponent is 2, so it's n is 2. And the derivative tells us, the rules for this tell us to take n plus 1, so 2 plus 1, now my exponent is 3, and take it all over n plus 1. So x to this becomes x cubed all over 3. Here, 2 stays the 2 multiplied out front. Same thing, the exponent is 1, so n plus 1. 1 plus 1, we now have an exponent of 2, so x squared, and it's all over that same number, n plus 1, so all over 2. And that 2 that stayed plus the new 2 we just put in the denominator cancel. 2 over 2 cancels to 1, so there's really a 1 multiplied out front of that. Okay, so just to recap. Here's our function. We took the derivative. This is the derivative of that function. And now, this comes from the integral, that 1 to 3. This integral, we have to evaluate it at 1 and evaluate it at 3. And we're going to subtract our output when we use 3 from the output when we used x is 1. Okay? So let's plug in what happens when you take, let's do 3 first. Let's do the big one. Big minus small. So 3 first. So 3 cubed is 27. 27 divided by 3 is 9. Plus, so 9 plus, and then plug in 3 also here. 3 squared is 9. 9 plus 9 is 18. Okay? And then we have our bottom one, 1. So x is 1. Let's plug in x is 1 now. 1 cubed is 1. 1 over 3 is 1/3. 1/3 plus, again, plugging in that 1 the other time we see x, so 1 squared is 1. 1/3 plus 1. 1/3 plus 1 is 1 1/3. And we're subtracting. When you evaluate an integral, you're plugging in your a and b, and you're subtracting the top from the bottom, the big from the small. So we evaluated when x is 1. We evaluated the derivative when our x is 3. And each of those are here. The 18 we just found and the 1 1 1/3 that we just found. Now this is just back to Algebra 1. How do you subtract fractions? Well, 1 1/3 we'll just change to 4/3, right? 3/3 plus 1/3, so that's 4/3. And then we want our 18 to have the same denominator so we can subtract it. So if we want 18 to have the same denominator, we're having 18 times 3 all over 3. 18 times 3 is 54. So 54 over 3 is equivalent to 18. 4/3 is equivalent to 1 1/3. Whew. Now we can subtract. We have the same denominators. 54 minus 4 is just 50. And so you have your answer of 50 over 3. And we're done. Okay, so that was example 2 on page 447 if you want to follow along. And that unit would be foot-pounds. So there's also, that reduces to 16 2/3 foot-pound. There we go. So that would be your answer, equivalent answer with units. Okay, so next let's move on to example 3. And we are given a spring. So a spring, think of like a mechanical spring, you have springs in your vehicle, you have springs all over your house, doors that open and close, you have springs everywhere, or even just think of a slinky. Well, no, sorry, not a slinky, because that's not compression. Think of a spring where you have, I'm just going to use this really quick. Okay, all right, there's your spring. If you're not touching it, that's what your spring, ignore the other notes on this paper. Reusing. So that's what it usually is. Now I can take it from that distance. That's where it is without touching it. And maybe I could push on it, use my strength and make it the distance a little shorter. Okay. Or starting that same starting position, not touching it, I could pull really hard and pull it apart a little bit. And I'm increasing the distance. I'm increasing the length of the spring. That's what we're talking about right now. Okay. So for this example, it's saying the natural length, we call it natural length, we'll say for this sketch I did, say its natural length is 10 centimeters. That's without touching it. It's 10 centimeters. I'm going to pull really hard and I'm going to get it to 15 centimeters and 18 centimeters. So here's our question. A force of 40 newtons is required to hold a spring that can be stretched from its natural length of 10 to a length of 15. How much work is being done in stretching the spring from 15 to 18? Okay, so our solution, we're going to use Hooke's law, and Hooke's law tells us it's just f of x equals k times x, and this is in your book. This is f of x equals k times x. K is just a integer, we call it the spring constant. The spring constant is a positive constant. I guess it doesn't have to be an integer, it could be a decimal, but often you'll see it as a integer that's positive, so a whole number. Anyway, k times x. So you've got a spring constant k as a positive constant. This is Hooke's law, providing, of course, that x isn't too big. I mean, there's a stretching capacity. A spring can't be stretched forever. There is a maximum that it can possibly be stretched. Okay. So Hooke's law, we've got Hooke's law there. And then we've got the problem gives us you're using a force of 40 newtons is required to hold a spring that has been stretched from its natural length of 10 centimeters to a length of 15 centimeters. How much work is being done in stretching the spring from 15 to 18? So I've written down that for the start of our problem. And we first have to use Hooke's law to find the constant that the spring is being stretched. So I'm plugging in to the f of x equals kx. So my force is 40, f of x is 40, and my k, this comes from, it has to be in meters. So if I went from 10 centimeters to 15 centimeters, right? I was stretching it here, we were at 10, and then I stretched it to 15. So really my distance I increased by 5. So it's a 5 centimeter is my the distance, but that's in centimeters. I want to go to meters, 100, divide by 100, so 2 decimal place change. So 5 changes to 0.05, okay, 0.05 there, and so that's our K. That's our distance that we've moved, 0.05. 5 centimeters coming from that, changed into meters, 0.05. 40 equals 0.05 times K. Solve for K, divide both sides by 0.05. 40 divided by 0.05 gives you 800. So our constant there is 800. Okay, now let's do the same thing. We've got the meter change. So when we go from 15, so it was at 10, we stretch it to 15. Now we're stretching. I have an invisible string here, right? Stretching. So then you go from 15, you stretch it out to 18. You're not just going from 15 to 18. When you're at 18, you have that entire force that's coming from 10. So it's really an 8. Don't do 18 minus 15, 3. It's 18 minus 10 to get the force when it's stretched to 18 meters. And so that's where we have this. So this is my A to B. I started my integral, started labeling my integral. So we're starting at 0.05 and going to 0.08. So that's our 8 centimeters. We're being stretched from its natural spot. So 8 centimeters converted to meters, 0.08 there. So that's our A, that's our B. On the integral, 800x. So f of x equals kx, and we know k is 800 now, so we can say f of x equals 800x. We're using that equation and what we just found, k to b. So you can write this. That's the work being done in stretching it. So from 15 to 18 now, we've started our integral here. We're going to plug in our function. So integral says, we take the integral and the function f of x. Oh, I'll rewrite it. Okay, I'm going to rewrite it here first. So this is this one. This is our formula that's given. So I've rewritten it down here. And now I'm going to replace f of x with what f of x is, 800x. Okay, so 800x dx, and this is telling me to take the derivative of that, so that's x to the 1, that becomes, my n is 1, so 1 plus 1, so now it's x squared all over n plus 1, the exponent was 1, 1 plus 1, so 2, all over 2, so that gives us x squared all over 2, and the 800 stays as the coefficient outside, so 800 times x squared divided by 2, 800 divided by 2 is 400, so we have 400 squared. Our derivative of 800x is 400x squared. Okay, so we have, that becomes 400x squared, and that's for, I'm out of space here, the integral. Okay, let's do this. So now we have to evaluate our integral, so we'd write it as 800x squared over 2 for 0.08 on the top, 0.05 on the bottom. So we have 400, and now in that x squared place, I have to evaluate it for the a and the b. So the 0.08 and for the 0.05. Okay, so then you're just plugging in. So here's this, you're going to let that equal x. So 0.05 is going to be an x, and that 0.08, you're going to let that one equal x. So you're going to plug those in. When we do that, we can reduce it. So that's not 800 over 2, it's 400 x squared. So x squared, what is 0.05 squared and what is 0.08 squared? Remember, it's b minus a, top minus bottom, big minus small. So 0.08 squared minus 0.05 squared, and then we'll multiply it by 400. Do that in your calculators now. Okay, and we got 1.56. And 1.56, this is our answer for the work being done. Our unit on work is joules. So let's label 1.56, capital J, our joule there, and we are done.